This talk will be on high-resolution CAM5 simulation of current and future climate. Will be given by Kevin Ree, Dr. Kevin Ree, from NCAR and also Stony Brook.
Awesome. All right, well, while this is loading, first I want to obviously thank the organizers for having me here. In addition, for this work, it requires a pretty large group of people to do, and so I've only listed some of the few that I've worked directly with, and this includes Julio Backmeister at NCAR, as well as my other colleague for a lot of these simulations was Michael Weiner, who was at the Department of Energy in the United States. So just a little background. There is a pretty large effort at NCAR and within the Department of Energy to develop the next generation high-resolution version of the community atmosphere model, which is the atmospheric component of the community Earth system model, which is the coupled version that is used for CMIP. Currently, at least for the foreseeable future, so the next few years, we're targeting a horizontal resolution of 25 kilometers globally. And for this talk, most of the results I'm going to show are really kind of preliminary and exploratory for the high res, but I'm going to initially show some results that some others have actually done on looking at precipitation in the high resolution version of the model, and then go into a little bit more detailed discussion of tropical cyclones, and then also look at some future climate scenarios. And then if I have time at the end, I'm going to make a push. So first of all, pretty straightforward, as we've kind of seen. We're using the AMIP protocol here for simulations using CAM5, and we're using now the spectral element dynamical core, which is the dynamical core that was implemented after the CMIP version of the model. And we're going to be running at 25 kilometers, as well as we have some 100-kilometer simulations for comparison. And this will be comparable to a previous version of the run that was run with CAM5, but with the older dynamical core of the finite volume. And we're going to be using the GFDL tracker for all TC tracks when we get to that point. So just to start off right here with resolution and show you what we're kind of working with beforehand. So over here I have the observations, and all these precipitation sides are actually courtesy of Julio Backmeister. And so this is for the kind of the CMIP 5 version of the model, slightly with a different dynamical core. But what we've kind of seen is this problem that's kind of well known, particularly within CAM, is that typically at 100 kilometers, the precipitation, it rains too often, but not hard enough. And as we go to high resolution, we actually really do, particularly if you focus in the tropics, we do see some improvement in frequency, but obviously not as much improvement as we maybe would have hoped for. And when it comes to intensity, it's actually kind of a mixed bag. So we do see some increases in intensity in certain areas, but we actually almost now are maybe biasing it in the other direction. And so one of the things we wanted to do is look regionally. And so here's just showing West Africa. And so down here is the observations. And we see that actually as we do go from the lower to high resolution, we do kind of see an improvement in the overall distribution of the precipitation. But actually when we go to North America, we don't really see the improvement that we would hope for. And so typically we see here that we're missing, at the 1 degree, it's pretty well known that we're missing this nocturnal maximum over the Great Plains of North America, and that is not improved at all as we go to 1/4 degree. So the first little case study that I kind of want to dive into here is some work that others have been doing at NCAR, and it kind of looks at these individual corridor events. So these corridor events are events in which you get pretty much most of the rain at night, and actually 68% of all mesoscale convective systems are associated with such corridor events. And so what we're going to actually do is we're now going to run the model with the uniform version at 1 degree or 100 kilometers. We're also going to run a uniformed one at 25 kilometers, and then we're going to see if the reason we're not getting these events here at 25 kilometers is maybe a resolution issue, or if it's maybe a more difficult physics parameterization problem to look into. And so, and additionally, we're going to run this kind of really exploratory resolution where we use this variable resolution mesh to get all the way down to 6 kilometers over North America. And the way these simulations are actually set up, these are different than the ones I actually just described. These are our nudge simulations that start on June 1st of 1998, and they're run nudged everywhere else besides this kind of box here that's also apparent in here. So they're nudged until July 18th, which is before the corridor event, and then they're still nudged out here, but within the domain they're allowed to freely go. So what we see here, this is just a comparison of the trim, so the observations, the 100-kilometer version of the model, the uniform 25-kilometer version of the model, and now this kind of exploratory 6-kilometer version of the model. And what we see is perhaps as we increase resolution, we are able to capture some of these type of events, but, and particularly maybe even more so as we go to 6 kilometers, but we can see that it's actually still struggling to really get the precipitation associated with such events. And so one of the things we're going to look at is the diurnal cycle to see if we can see anything from here. So we're now going to use the average within that pink box up there. And what you see here is to orient you, this is midnight here. So this shows you this kind of typical thing that we do see where we have this maximum in the middle of the night due to the rain. And what we see in general is if you look at all versions of the simulations, none of them are really capturing this. The solid lines here represent the total precipitation, and the dashed lines represent the precipitation that comes from the large scale or the resolved precipitation in the model. And so one quick thing to notice is that the difference between the solid line and the dashed line then would be the parameterized convection precipitation. So the one thing to see is if you maybe follow, especially as we get to 25 kilometers, if you follow the large scale or precipitation, so the dashed lines, they maybe do capture somewhat of the diurnal cycle that's expected, but we have this huge bias that during the day we're getting too much rain, and it's almost all coming from the convective parameterizations. So this tells us that maybe going to high resolution isn't buying us what we want. There is some question. We're still using the deep convection scheme here at 6 kilometers. So there is some question as to whether that's helping us, but we can see that we're not going to solve the problem necessarily by just going to higher resolution in the current context of CAM. And one other thing that we look at is now more generally Midwestern precipitation. So this is now the same simulation. We're just now showing 31 days worth of averages. And so now we're just going to look in this bigger box and kind of see how it's doing with precipitation overall. We do see that as we go to higher resolution, maybe we are certainly capturing kind of the variability a little bit better. But again, if we see this typical structure of the diurnal cycle, we can see again, if anything, it's almost worse now. So as we go to high resolution, maybe the large scale scheme, which is again the dashed line, is capturing some time of a maximum at night. But you can see that if anything, these are 31-day averages. So if anything, the convection scheme it's almost surprising how much it's doing. And so one thing we did want to test is we actually ran the model at the 6-kilometer mesh without the deep convective scheme. And so we do see that if you were to follow kind of the dashed line here, we do kind of see that this does help to improve maybe the diurnal cycle attitude, but we do still get a lot of convection happening at night due to the shallow convection scheme. So just a brief recap, not everything is improved with resolution, which isn't too much of a surprise to us after we've been doing this for a while. The large-scale precipitation has approximately correct diurnal cycle, but it's definitely of the wrong magnitude. And parameterization of the parameterized precipitation from convection is almost always nearly 100 degrees out of phase. And so now I kind of want to move away from that and switch into tropical cyclones. And the first thing I'm going to show is I'm going to put these new versions of the model, the spectral element 25-kilometer runs, into context by comparing them with the previous versions of CAM. But in general, the CAM has shown to have some skill in simulating tropical cyclones. This is shown, I'm going to show real quick with idealized tests as well as decadal simulations with CAM5. But there is, as you'll see, much room for improvement as there exists some pretty large biases in a lot of these things. And there is this kind of one thing, and these why a lot of these simulations thus far are kind of what we call exploratory in the sense that there is a lot of uncertainty to the tuning of the model, particularly at these resolutions, because we can only, at this point, afford to run one realization or maybe a couple ensembles, so we don't have the time to tune the model like we typically would at 100, we did at the coarser resolutions. But also there's actually this interesting thing is there's this uncertainty to a lot of these parameterized processes, these tuning knobs, and actually the impact they have on the extreme events. So it's kind of take us all with a grain of salt, I guess. The first thing I want to show is these idealized simulations that we've been doing for quite some time now. And what this is showing you, so this is not an AMIP simulation. This is an aquaplanet simulation where the entire globe has the same surface temperature, and it's bogus with an initial vortex that's really broad and weak. So it's basically developed it's basically built to develop into a tropical cyclone. So if the model is capable, it will develop into a tropical cyclone. And so what we can see, we found early on that actually as we go to higher resolutions, CAM in its current format with the parameterizations that were maybe developed for a much coarser version of the model is capable of producing tropical cyclones in this idealized context. And there is some realism to them, so it's not like they're completely off. I mean, the scale of them is certainly much larger than observations, but just it passes the eye test, so they are doing what we expect. And this is really one of the ways that we've tried to analyze the impact of model design choices on how well the model does at simulating tropical cyclones. So what I'm showing here is, again, this idealized setup. So this is similar to this previous slide here with the run, but now it's showing snapshots, and these are at 25 kilometers using the finite volume version of a slightly older version of CAM. And so what this is a snapshot looking down on the storm of the wind. Here is a snapshot through the center latitude of the storm, and it's a vertical cross-section. So what this does is it kind of shows this vortex does develop into a tropical cyclone by day 10. And this has really nice characteristics, because the advantage of this is we can run the same simulation with the newer version of the model, which has wholesale changes to the physics parameterizations. And what we can see is now with a simple idealized test, we can try to look, and if I toggle between these, we can look at the impact of the convection scheme or all the other parameterizations that were changed. So what we did see is actually a CAM4 was notoriously known. If you tried to run an AMIP simulation, it struggled in creating cyclones, particularly at 50 kilometers. And CAM5 is a scheme that basically due to a lot of convective changes in the boundary layer and shallow convection scheme, it's actually able to simulate tropical cyclones, and you can see this from this simple test that runs for 10 days, so it's a fraction, pennies in a bucket of costs to actually understand the impact as we go to these resolutions. And this is just one last slide I want to show on this. And the advantage of such idealized tests is you can run ensembles, so you can get a grasp for the spread in the simulations. And we can see this, there is this very clear impact of resolution on tropical cyclones, which is obvious to most people in this room. So as we go from 1 degree to quarter or half degree, we can see that these storms are allowed to develop, and they develop deeper. But the interesting thing is that when you switch between models, that resolution dependence can be very different. And so this simple test kind of gives us an understanding of how the model would behave. And so when we ran a CAM5, so we ran the same version of the model, and we ran a 26-year AMIP simulation, it was no surprise that when we run at 1 degree, we get very few storms on the globe. And if we go to quarter degree, that climatology changes quite drastically. And so this is just a typical plot here showing, actually I've cut it off at tropical cyclones, or tropical storms. So it's basically all hurricanes. And the color so the redder colors are the more intense storms. So what you do see, the first thing that should jump off the page is at 25 kilometers with CAM5, we are able to reproduce category 5 storms. And you can see we're, in general, if you compare it to the observations, we're doing reasonably well in location. CAM5 has this large bias here in the Central Pacific where it's producing way too many storms. And so we're still trying to understand a lot of that. But the first thing I really want to spend some time on is actually the impact of a dynamical core. So one of the things that happened after the CMIP versions of CAM5 is we switched from a finite volume version of the model to a spectral element version of the model. And one of the main motivations for it, at least in NCAR's perspective, is that the finite volume version that we were using was on a regular lat-long grid. And as we were trying to push these out into more and more processors, this spectral element version was on a cube sphere, so that helped improve scalability, and as well as other reasons of why it was switched. And so what this initial plot here shows you is that in general, CAM is producing slightly less number of storms. These values are somewhat sensitive to parameters in the tracker that we're trying to quantify. But we can see that as we go to hurricane strength storms and major hurricane strengths, it's very clear that the spectral element version of the model is producing more hurricanes and more major hurricanes. And so one of the things we've tried to maybe look at is why that is. So I'm going to take a second on this plot because it's quite busy. But what I'm showing here up top is, so this is the CAM5 FV version, so the previous version. This is kind of the new version, current version of the model. And this column is the differences. And what I'm showing here is the potential intensity. So this is the average. So it's the maximum potential intensity, which is a theoretical intensity for how strong a tropical cyclone could get based on its environment. And I'm taking the annual maximum, so the month that has the highest maximum per year, and I'm averaging over the entire 26 years of the AMIP simulation. And so what this is meant to do is kind of show you to see if there's a difference in the large-scale environment within the two versions of the model, and if maybe that's reason why it's producing different number of storms or intense storms. And what we see right away is that, and so this is CAM5 FE minus CAM5 SE, which is a difference. And so what we see here is that CAM5 FE has an environment within it that is more conducive to creating intense storms. That doesn't necessarily mean that the storms will get that intense, but it's more conducive to intense storms. And if you go back, that's kind of interesting because if you look here, it's actually the other model that's producing the most intense storms. And another thing we've tried to look at is this Genesis Potential Index, which is an index that was created by Emmanuel Nolan. The way you can kind of think of it is this is, you know, like if it's 8, then there's predicted to be roughly 8 storms in that area per year, or at least that form in that area per year. But when you're trying to compare these, it seems a little difficult to really check out the patterns. I mean, it seems that one thing that we do see is that the SE version seems to have a lot more potential for producing storms in the Western Pacific, but the FV version is definitely more conducive to producing storms, particularly in the North Atlantic, the Eastern North Atlantic. And that's kind of holds through if we look down here. So now these are density plots. So this is the Genesis density and the track density for the actual track storms in the model. And what basically this represents is whenever a storm or forms or goes through any space within a 5-degree radius of any given point. And what we do see is that CAM5 FE is producing more storms in the North Atlantic, but in general it's producing less storms in the Pacific. And we're still trying to dive into why this is. It's not necessarily the most straightforward. And one thing I do want to comment on here is that there is one other difference between these two models. It's not just a dynamical core. There's also a difference in the aerosol model. And if we've done extra simulations, and if you run this version with the same aerosol model that we see here, then the difference in the large-scale environment actually decreases, and they're roughly the same, which shows that the treatment of aerosols in the older version is what's creating the environment that seems to more be conducive to intensity, but it doesn't actually impact the actual storms that develop, if that makes any sense. If you have questions about that, I can talk about that offline. But one of the other interesting things here is that we've looked at, so this is a PDF of intensities. And this is also a plot of the surface pressure, maximum surface pressure, minimum surface pressure versus the maximum wind speed. And we do see that at least in the more weaker storm range, both versions of the model seem to track pretty well with observations, which is the black line. And these are supposed to be black dots, but I don't know what happened. But we do see that as we get out to these more intense storms, they're both underestimating perhaps the speed given a pressure, and the FV version is maybe doing it even more. And that's kind of apparent if you look at the PDF up here. You do see that there is this large increase in intense storms with the spectral element version of the model. And I'd like to just kind of take us back to when I was showing you these things with the idealized tests. That's exactly what we saw with the simple 10-day test that's a fraction of the cost. We actually saw that in all cases, the spectral element version of the model is producing more intense storms. So we could have gotten to that result with one fraction of the cost as opposed to running a full 25-year simulation. So this is kind of just gives credence to the fact that the simplified models are working. And this just is kind of also shows you that the differences can be really complicated as we get into individual basins. So here we can definitely see that the CAM-SE is producing less storms in the North Atlantic. And it's partially due, there's this delayed start in the hurricane season, which is definitely contributing probably to the less number of storms. So now I kind of want to jump to our future climate simulations. So now we're running the same version. Now forget about the impact of the dynamical core. We're now running the CAM5 SE version. And we're going to do 2 time slice experiments with RCP 4.5 and 8.5 for 20 years. And the first thing I want to show is just look at briefly at the differences in precipitation. So we see as we go from the present day AMIP run to 4.5 and 8.5, there's increases in intensity in the precipitation, and there's definitely an increase in the mean precipitation. And what we do see is there's also, as maybe one would expect, there's also this increase in intensities. So as we go to the warmer climates, we are shifting in the precipitation. But what I want to talk about the last few minutes then is the impact on tropical cyclones. So what we do see here from this same plot is that as we increase, as we increase to warmer climates, we see that the total number of storms is reducing, as well as the actual number of hurricanes. But maybe the number of major hurricanes, so category 4 and 5 storms, is remaining somewhat unchanged. All the variability, at least within these models, seem to be all rather consistent. But if we look at a PDF, obviously just looking at kind of arbitrary divisions of intensity doesn't really show us too much. And what we do see, as a lot of other groups are seeing now, is as we increase, as we go into the future climate, warmer climates, we do see this increase in the most intense storms. And if we look particularly at the North Atlantic, which is of interest to us, we do see, again, similar results. We see a decrease in total storms and hurricanes, as well as some changing in the storms, in the seasonality of the storms. So some final thoughts on this. The impact of the dynamical core on tropical cyclone statistics is rather significant. And this needs to be explored more, and I don't think it can be understated in the sense that I think a lot of modeling groups take into account when they switch out a new dynamical core that they don't think that it might impact your ability to simulate localized events. But it certainly does, and it's maybe just as important as changes in physics parameterizations. And the CAM-SE and FV both produce less tropical storms per year than observed, and CAM-SE is producing more than CAM-FV overall, or hurricanes, that is. And we need to focus, we're just digging into this data now. And so with my last few minutes, I kind of want to kind of take a little sidetrack and try to explain maybe where some changes in development can be made to help us improve these models earlier on in evaluation. So the typical way that we evaluate GCMs right now in the community is when we're first initially developing a dynamical core, we first build it in shallow water, and we have some test cases that we can evaluate them. And then we do these 3D dynamical cores. So we have a 3D dynamical core, and now we use this other determining test, some that SJ showed that for other modeling groups, in which you can look at baroclinic waves, or you can look at flows over a mountain. And then the next step that we've made up to this point is we then run 3D aquaplanet simulations with full physics parameterizations. And then we go on to these AMIP style, which we can then compare to observations, and then we go even further to coupled models. And there's this huge missing part here. And so what we've proposed now for numerous years, starting back to a paper I wrote a few years ago, is that there's this huge missing link within the community of which we can actually try to understand as we make model advances, and we just add some simple moist physics that we can actually understand how the model does, or how the dynamics and stuff are impacting the simulation of these events earlier on in the simulations. So the idea is just, if you can think of this as what an atmospheric model looks like, so what you do is you take your dynamical core, and then you add a couple processes, much simplified, that are important to the process that you're interested in, which for me has been tropical cyclones. And so you can do these simulations with 200 lines of physics code, and you can actually make pretty robust comparisons across different dynamical cores. And so what this is just showing us, again, which is what we saw with the AMIP simulations, is that the spectral element version of the model is always producing stronger storms than the finite volume version. And that can be seen for running the dynamical core with 200 lines of physics code. But this doesn't stop there. We've done some work with the dynamical core intercomparison project, which other modeling groups have done the same thing. And so we can start to see that this is a good way to maybe, in addition to running AMIP simulations, help to compare across models and the impact of dynamical cores on idealized events. But this isn't just limited to tropical cyclones. So this is some other work that we've been doing, and this is will be my last slide here, in which now this isn't a simplified physics, but it's still a reduced complexity test bed. So what we're doing here is we're running the model in aquaplanet mode. So this is the full version of the model. But what we've done is, so we've gotten rid of land, we've gotten rid of all gradients in insolation, and we've gotten rid of all gradients in SST. So basically, we have now formulated the model to look basically like a large domain limited area model. And what it actually helps us do is now we've simplified a lot of the processes, so we can actually try to understand the impact as we go from the lower resolution to the higher resolution, and the impact that has on extremes. And we can actually, in a more controlled sense, dive into it. And so, you know, we can start to actually look at these PDFs of precipitation, and we can start to look at how the clouds are behaving, at least in radiative convective equilibrium, which is a decent approximation of the tropics. So it's actually proven to be quite useful. And we can do the same thing in a uniform rotating world, which is some stuff that Isaac Held has done at GFDL with a large area limited domain model. But now we're just doing the same thing in spherical coordinates. So what you basically have here is every place is rotating like it's at 10 degrees north. And so the solution to radiative convective equilibrium with rotation is tropical cyclones. And so this gives us an ability to actually understand the impact of resolution on tropical cyclones within the model. So just to finish up, the impact of the dynamical core on tropical cyclone statistics for decadal experiments is significant. Not all biases improve when we increase resolution. We are currently in the process of doing ensemble simulations at 25 kilometers, both with the SE version and the finite volume version, as well as trying to use different techniques for how we prescribe the time slice experiments. Maybe the last one is reduced complexity test beds can help provide an opportunity to evaluate these kind of next generation high resolution versions of the model much earlier in development, and actually maybe help us understand our results a little bit better as we get there. So thank you.
Hi. Thank you. Okay, just say.
Yeah, I have two questions about cyclone simulation. If you go back to one of your earlier slides on intensity,
Yeah.
Showing the sea level pressure versus time, it looks to me that the intensity from the SEM is just too strong.
Yeah.
The sea level pressure was something like 840, mini bar.
Oh, yeah, for these ones?
Yeah, go back.
Yeah, right here.
Yeah, here.
Yeah.
This is just not physically not possible.
Yeah, absolutely. And so this is, if we were to run this, if I was to actually run this same exact simulation with the current version of the model, it would definitely not be as deep. So this was one of the ways that we found out that maybe the way we were doing it initially is there was some issues that needed to be fixed.
So you are tuning.
So the idea is
dissipation.
you can use these reduced complexity test beds to help you to tune the model earlier, at least make more educated decisions on the tuning.
Yeah, this is idea right now. The other remark I had is about the AMI simulation, which you show that SEM has simulated a little bit more hurricane or tropical storm than the FV. And both are a little bit under the surf, right?
Yeah.
But if you look carefully, I look carefully that SE is doing the wrong thing to compensate. That in the Atlantic is fewer.
Yeah.
It simulates fewer hurricane than than the FV. And
Right.
On the Atlantic, it's making more hurricane to compensate for the total number. So the correlation is much worse if you look at it.
Yeah, absolutely.
Yeah, even though the total number seems to be a little bit, the bias is smaller, but the correlation will be a lot worse than FV, which I can tell.
And we suspect that actually, maybe to be fair, that some of these differences in the North Atlantic are actually due to the fact that there is a difference in the aerosol models. So if we were to run the FE with a similar version of the aerosol model that we use in SE, then the Atlantic storms look much similar to the SE. So they kind of look similar, which, that means that other things are happening differently in other basins, but yeah.
So these two are not orange to orange comparison?
Yes, but these are not necessarily apples to apples comparison, but they are versions of the model that we've been using, so it is somewhat good to do. Now, if you want to, we've now running the simulations when we're making sure we are using the same exact aerosol model, but the results on intensity are independent of the aerosol model. But but interannual variability, as one would expect, it does have some impact, absolutely.
Yeah, that's true.
Okay, Sugi-san.
Can you explain why and how the difference in the dynamic core affect the tropical cyclone simulation? Does it affect on the divergence damping or something like that?
So that's one of our so we are just now starting to do some additional simulations in which, maybe to the surprise of some in the room, so the actual version of the SE dynamical core that we're using is more diffusive than the FE version. So that's one of our theories, is that maybe that is impacting it. So actually increasing the diffusion is actually allowing them to develop. So having it be more diffusive, is allowing them more to develop. But we're just now starting to test that by changing the divergence damping. We were like 1 year into a run. So I can't, I guess, actually say what we've gotten from that yet.
And one more question is about you showed that the SE version have more tropical cyclone on the Atlantic.
And in the Atlantic, it has less.
Huh?
Less.
Atlantic less.
Yes.
And in other parts more.
Yep.
So why?
Maybe
Can you explain?
No. I think that. I don't know. I had another plot. Oh, maybe I don't have it. It's not necessarily clear why that is. So if you look here in tracks, there's definitely an increase, so SE has less storms, which is what the red is in the North Atlantic, and pretty much more storms everywhere else. And so we do think that there is, in fact, there's a slightly uncontrolled difference between the models, and that there are differences in the aerosols, slightly distribution. But we actually see, if I was to show you a plot of the aerosols, actually, the largest difference of aerosols in the model actually occur in the North Atlantic here. So, why these differences are there, I'm not even quite sure yet.
Okay, last question from Min Chao.
I have a question about the diurnal cycle. Did you check in the tropical land, do you see an improvement of diurnal cycle?
In the tropical?
Yeah, like the Amazon or Africa.
I haven't.
Since you choose probably most challenging location.
Yeah, we chose the most challenging part, and that's mostly because, particularly for us, that's of interest. But I didn't do it, so I don't know. I'd have to. I'm sure somebody might have though.
Okay.
Sato-san.
Yeah, just a quick. Yeah, what's the vertical resolution? Do you usually use 30 levels for CAM5 SE?
Yeah. So all of these are run with the same number of levels, which is 30, and they're all use the same vertical discreditation. So it's all based off the Lagrangian approach from Lin 2004.
Is that the standard vertical levels for the CAM?
So you mean like in terms of distribution?
Yeah, no, vertical level 30.
30, yes, 30.
Yeah, I think it's a little.
It is a little low compared to other groups.
Yeah.
And so as we develop CAM6, one of the things that definitely will be changing will be the number of levels.
How many?
I think they're testing a lot of different ones right now, anywhere from 45 to 60.
Okay, thank you. We have to move on. So the next talk will be